Well, everybody must be spending time with family and enjoying their Thanksgiving weekend because I'm the other one here. So that's quite all right. I'm going to get going. So today I'm going over the rectangular coordinate system and graphing. So this corresponds with section 3.1 in our textbook. So I just want to start with reading and interpreting data. So data is just basically when you're collecting numbers and information that are in number form, or numerical, as they say. So data is when you get a whole bunch of data, you're usually presenting it in a table or a graph. And it's usually a lot easier to read and understand when you see it in a graph because you get an idea of is something increasing really fast or slow, or is it like making waves, like going up and down, up and down, up and down. You can kind of see it looking at a table, but it's harder to see just what the shape looks like if it's not graphed. Like here I have a table, number of bachelor's degrees. I think these are in, I don't know if these are millions maybe. And in table form, you can say, oh, okay, the values are increasing. But when you see it in a graph, you're like, oh, it's actually forming a line. So it seems to be about increasing by the same amount each year, which is not something you would necessarily get by looking at the numbers themselves. But the graph, you can see that it's basically forming a line. So when we're reading graphs and tables, it's important to understand what what it means so that you can read it properly. So when you're given a table, you have two columns, and the first column is always your input, and then the second column is always going to be your output. So if you're creating data, that's how you want to create your table, so that the first column is what your input is, your second column is your output. When you have a graph, the horizontal line, or the horizontal part of it, which we call the axis, is always your input. So your input is always graphed horizontally, and then your output is always graphed vertically. That's really important. It makes a difference in how you read the graph. So you want to make sure your input is always horizontal, output is vertical. These input values I'm talking about are called the independent variables. So if you've taken a science class, you may have heard this term before. Any kind of statistics, you talk about independent variable, if any kind of studies, these are the things you don't control. A good example is time. When we graph, we often graph things against time, like number of months, number of years, number of days. Time is a very common input variable. It's always the input because we don't control time. Time just happens. It's independent of anything that we do. So that is always your input. And as such, that means it's always going to be horizontal, or basically your first column in your table. The output values are called the dependent variable. So these depend on what the independent variable is, hence the name dependent. We don't control what the outcome is. This is things that are just happening, or we're observing, or counting. So if something's happening per year, we don't, we're just like, oh, okay, what was the output for this year? If you're looking at stock prices or something like that, or revenue, you're not, there's controlling it to some aspect, but it's more of like an outcome for that year. So that's the dependent variable, and their values depend on what your input is. So they change based off of your input. So there's a relationship there. That's why it's called dependent, because their value depends on the input. So the textbook actually has a lot of great examples. So I've just grabbed them and we're going to work through them. So this is problem 2 in section 3.1. The number of Botox injection procedures in millions in the United States over a 6-year period is shown in the graph. So we've got 3 parts here, and I just want to talk about the graph before we read the parts. So if you look at the graph, we've got a title, and it tells us what we're graphing. We are graphing the number of Botox procedures in the United States. So we want to be very specific, and it's telling us the units, that this is in millions. And you look at our horizontal, we've labeled that these are years. This is a 6-year period, so it's counting. You notice that we don't have 1 through 6, it's 0 through 5. So the first year it's counting as year 0. So it is 6 years here. We're just starting to count at 0 rather than 1. And then a vertical, notice what we're counting by. We're going from 0 to 0.5 to 1. So we've got this set spacing. And we have to, it doesn't have to be the same. You don't have to count vertically the same amount you're counting horizontally. Like horizontally, we're counting by ones, but we're counting by halves going up. But within that scale, you need to be consistent. So I can't count from 0 to 0.5 and then to 5. Like they need to be the same spacing. So we've got that going on. And then we've got a label, number of procedures, and then again, it's telling us that the units are in millions. That's really important to give context. So labeling, telling you what you're measuring, what is your horizontal, what is your vertical, what is your title, that's context. And it's including our units so that any numbers we read are measured in millions. So let's look at part A. For which year was the number of procedures the greatest? So the largest number on our graph, we're looking at this value right here. And so that's the highest number, because if you look at vertically, that's closer towards the, the low numbers are in the bottom, the high numbers are on the top. It makes sense, low to high, that the bigger it is, the higher it's going to be, like a mountain. And so that is the number of, that's the highest, and so we want to read the year off of that. And so you just work your way down, and that gives us year 3. So we don't know the actual year or anything, like they haven't given us any of that information. We only know what we can read off of the table, and it says year 3. So year 3 has the number of procedures being the greatest. Part B, approximately how many procedures were performed in year 5? So you're going to go to year 5 on your horizontal, and then we're going to look at where the dot is, because that's what we're graphing here. So it's right here. It says approximately, so that means you have to kind of estimate or round. It is almost on the line, and the line, if I follow this line here, that it's almost touching horizontally, is at 3. Which with units is millions, so that's 3 million. So we can approximate this to about 3 million. So we're just going to, we don't know the exact number, but it's close enough. So we're going to just say that's about 3 million. It's really close. That's the best we can do off of our graph here. And then we've got our next question. In which year corresponds to 2.3 million procedures? So 2.3, I have to sort of estimate, is somewhere about there. Halfway between 2 and 2.5 is 2.25. So you need to sort of know your fractions and those divisions. So if I work horizontally, this is a really terrible horizontal line. Doesn't look horizontal at all. Let me try that again. Okay, that's a little better. I hit, there's only one point horizontally that I hit, and so then I'm going to go down to read what the year is for that, and that's going to be year 1. So year 1 is about 2.3 million procedures. And so that's how you read a graph. You have to know what you're looking at. Are you looking at the vertical, or are you looking at the horizontal? And you have to understand what you're reading, and you have to include your units. But that's how you read it, is you look for the information you have, and then you basically are working horizontally and vertically. And you can see that it's sort of forming these rectangles when I'm like drawing these pictures here. So that brings us to the name of the system that we use to graph, and it's called the rectangular coordinate system. You can see that because I was sort of forming some rectangles with my highlights. So the other name for this system is called the Cartesian coordinate system, and that is named after René Descartes. He was a philosopher, mathematician, did tons of things. I think he was the guy that said, "I think, therefore I am." Said it in Latin, ergo cogito, ergo sum. So, fun fact, I took Latin in high school. So, but it's called the rectangular coordinate system. The center point, which is this point right here, is called the origin. Because every place we start in the center, and that's where everything is considered zero. So we start at zero, and then we either move from zero towards positive numbers or negative numbers. And so it's the origin, it's where we start at. Then these lines that we have with the arrows on, those are called axes. So the horizontal is called the x-axis. So plural is ES, singular is IS. So the horizontal is X, and then the vertical, you can see I've already got that labeled up here. That is the Y-axis. It's typically alphabetical order, so X comes before Y, horizontal, and then vertical. One way to remember this is Y's up. Y's up. Basically, to remember that Y is vertical, just tell yourself Y's up. And the graph here, you can see that with that solid line for the axes, it's divided into basically 4 sections, and those are called quadrants. Quad means 4, so that's where the word quadrant comes from. And notice the labeling that it's counterclockwise. And this is just by nature. The first quadrant is the one we're in most often, where both values are positive, and so that's the top right. And then we could have some negative inputs, so that moves to the left, and then we just follow counterclockwise from there. So that's how we label the quadrants, counterclockwise, starting in the top right. So points, the things that we graph, the little dots that we graph, are named using ordered pairs. So they're called ordered pairs because it's a pair number and they're in a specific order, hence ordered pairs. The ordered pair is X, comma, Y. Again, think alphabetical order. X comes before Y in the alphabet. And when we plot points, we go horizontal and then vertically. So we always do the X first and then the Y, though you could go the other way around, but we typically don't. So like if I was moving to 4 and then let's say I moved up here to 4 on the Y, let's see, actually let's make it look like a rectangle. So let's go to 5. It forms a rectangle. So if I was to put a point right here, our X value is 4, the Y value is 5. We write it in alphabetical order, 4, comma, 5. And so the X number that it lines up with first, and then the Y value that it lines up with goes second. And then you can see that forms a rectangle shape, hence the rectangular coordinate system. But generally, when we graph it, we only graph the dot. We don't graph the rectangle with it, but you can use that to help visualize the label for it. So let's just do some practice of plotting, and then we're also going to label what axis they're on, or if they're not on an axis, if they're in a quadrant. So it cannot be both an axis or a quadrant. It's going to be one or the other. So 4, comma 2. I'm going to just label these with letters. Choose a color other than red. So if I label them with numbers or letters, that will make it easy just to label them on my graph. So we'll just name them A through G. So A is 4, comma 2. That's how we read it out loud. The parentheses are just, whenever we write ordered pairs, they're always in parentheses, but we don't read that out loud. So we just say 4, comma 2. So that's 4 on the X. So I find where I'm at right there. And then 2 on the Y. So I kind of visualize, make sure I'm lined up. And then I label that as point A. B, we have negative 4, 4. So you start at the center. Negative means you go to the left, negative 4. And then the second value, 4, means we're going up to 4. So I need to make sure that I'm kind of lined up there. It's not going to be perfect because I'm hand plotting these. But you want to make sure that if you eyeball your rectangle that you're at the right X and Y values. Then C, we've got -3, 0. So 0 means I'm not moving up or down. I'm staying where I'm at horizontally. So that is on the x-axis. So I'm going to just choose a different color here. That is on the x-axis because we didn't move it up or down because the y value is 0. D, we're at 0, -3. So you start at the center. The first number means 0, meaning you don't go left or right. And so then we go down to -3. And so that puts me right here. That is D. And that is on the y-axis. This is actually on one of the lines. E, we have -4, -2. So I start at the center, and I go left to -4 because that's the first value, and then I go down to -2. So that's E. F, 0, 0, that is the origin. That doesn't have any points, so that is special. That is the origin. So that is on both the x and the y-axis. It's on both of them because it's at the intersection. And then G, we have 5. So I'm going to go to the right to 5, and then -4. So I go down to -4, and that is G. So now let me go back in. I labeled all the axes, which were on the x, which were on the y, or on both. Now let's go in and take a look at our quadrants. So A is in quadrant 1. So if I label these, that's 1, 2, and we always use Roman numerals for our labels. So A is in quadrant 1. And sometimes I just abbreviate that Q1. B is in 2, so I'm going to just label that as Q2. We've already labeled C and D. E is in quadrant 3. And then G is in quadrant 4. So if it's in the space, it's in the quadrant. If it's on the line, it's on an axis. So now with that knowledge, let's combine ordered pairs with reading a graph. So again, this is from the textbook. This is number 5. The price per share of a stock in dollars over a period of 5 days is shown in the graph. Now notice below, this time 5 days, we are starting to count at 1. So it's really important to know where you're counting. When we had the 6-year period, we started at 0. Here, the first point we have is at 1. So part A, interpret the meaning of the ordered pair 1, 89.25. So the meaning of an ordered pair comes from our labels on the graph. So our point 1, 89.25 is right here. So we interpret the meaning, we always do x first. So the x is at 1. So this is on day 1. So when we interpret our meaning, that's what we say on day 1. And then what are we graphing? We are graphing the price per share in dollars. So I need to say that. The price per share in dollars. And then I want the y value. So the y value is 89.25, and those units, that's the price. So that's, I mean, our label, our title is telling us what it is. So the price per share in dollars is 89.25. So $89.25. That is the meaning of the ordered pair. So it's not just a set of numbers, they actually have a meaning associated with based off of the units and what you're graphing. And when you're interpreting the meaning, you have to state that, including all of your units, the context, because the order pair itself without context doesn't mean anything. You need to put it in sentences. When it says interpret, that means you're writing a sentence telling us what this means. You're translating something from math back into English, essentially. So part B then says, what was the change in price between day 3 and day 4? So I'm going to just grab a different highlighter color. So day 3 to day 4, our price is the Y value, because that's what we have labeled on Y. It's 91.25, and then we go to $93. So the change in price is the difference between those two. So you can do 93 minus 91.25. And I've never been good at subtracting decimals, so I always use a calculator. So that gave me 1.75. So the change in price between day 3 and day 4 was $1.75. So remember, our units here are dollars. That's what it tells us. So that difference, that's how much it changed by $1.75. Now part C, what was the change in price between day 4 and day 5? So day 4, we're at 93. And then day 5, 90.25. So again, we are subtracting, and we're always doing the day 5 minus day 4 minus day 3. So it's always the most recent minus the previous, or the first ones. Day 5 is more recent. So it's going to be, let me just do this in a different color font, so we don't get too confused, 90.25 minus 93. So this is going to give us a negative, and that is indicating that it decreased. But the actual change is a negative $2.75. I'm not really sure when we deal with negatives if we put the negative and then the dollar symbol. I guess that makes more sense. The negative outside the dollar symbol. But the change is negative $2.75. Now, if it asked you how much it decreased, you wouldn't include the negative because the negative is telling you that it's decreasing. So if they already give you a word in there that indicates negative, you don't need to include it again. But in this case, they just say the change, so the sign has to be included. And so that's a negative 2.75. This one is problem 25. And so we've got a map of a park is laid out with the visitor center located at the origin. 5 visitors are in the park located at points A, B, C, D, and E. All distances are in meters. So they're telling us the units. They're telling us we've got this map. We put visitor center at the origin. Maps are a very common way to do graphs. GPS coordinates usually are latitude and a longitude. And so latitude is X, longitude is Y. They basically take the Earth and they put it on a flat surface, a flat map. We flatten it out, and then we basically have a 2D grid, and that's how we graph. It's the same thing. There are positive, there are negative GPS coordinates. So that's an example of graphs, basically. So A says estimate the coordinates of each visitor. It says example 3. Obviously, we don't need to go look at example 3. I'm going to talk you through it. And then B says, how far apart are visitors C and D? So estimating the coordinates means we're reading the graph and we've got the points. Now we're trying to figure out the ordered pair. So we'll just go in alphabetical order. So A. So I look at point A and then I want to read the X value. So it's in between 300 and 500. Now notice from the center that the first box here is counting to 100. That tells us that every box or every grid mark here is 100. So that means this is 200. This lines up with 300. So that means A is at 400. So 400. And I'm going to put an M for meters just to include units, but it's not necessary. But M is the abbreviation for meters. And then I want the Y value. So the Y value actually lines up exactly here with 200. So A is 400, 200. So let me erase my little marks there. Let's go to B. So B, remember that each thing here is counting by 100. So B is between 100 and 300, and it's halfway, so that would be 200. And then if I go horizontally, I have to estimate where I'm at. And we've got a negative 100 and a negative 200. I'm about halfway between those based off of my line. So I'm going to estimate that as negative 150. So you're just estimating. We usually estimate to easy numbers. There's no reason for me to estimate that as negative 149. It's just, you want to make them easy numbers, so negative 150. C. So we've got our X value here, which lines up with negative 300. And then my Y lines up with negative 200. So that I can just read directly off of our graph, essentially. And then D, I do my X value first, lines up with negative 300. And then my Y value, I have to estimate. It looks to be halfway between 200 and 300, so that would be 250. So I'm just estimating halfway. And then our last point, E, is nowhere on the X or Y. It hasn't moved, so that's 0. And then it's halfway between 400 and 500, so 450 is the halfway point there. And so that would be that ordered pair. So that's A, estimating the coordinates of each visitor. B says how far apart are visitors C and D. So that is the distance between them. So we're looking for the distance. How long is this line between these 2 points? And so you can count, well, how many boxes did I go through? And each box is worth 100. And you can count those. Or you can subtract your Y values. So D is at 250. And we always subtract top minus bottom on a graph like this. And we are subtracting. And then the Y value for C is negative 200. So we have 250 minus negative 200, so that is 250 plus 200, and that gives us 450. And then this is distance, so we need our units. And so they are about 450 meters apart because those are our meters, or our units. Mary, I see that you have joined in. I have only one more example left because it started at 1:30. So
I know, you know, it's 2 hours behind, and so I get caught up, and then I realize, oh my gosh, I have to do it now.
Well, you can watch the last example, and then you'll probably want to go back and rewatch the beginning.
Oh yes. Oh yes. Thank you.
Yep. Okay, so this last one, this is problem 31 in section 3.1. This is one of the ones that they want you to spend some time thinking. So the data in the table give the percent of males and females who have completed 4 or more years of college education for selected years. So selected years just means they picked some years. And if we look at the table, We've got 1960, 1970, 1980, and it looks like it's counting by tens, but then we have 2005, and that's not counting by tens. So you want to be very careful because we're not just counting by tens here. We do have some that have gaps of 5. Then it says, let X represent the number of years since 1960. So this is something that happens a lot when we are graphing, is instead of making X the year, we start counting at 0 and make 0 the first year of data, and then we are basically counting how many years after that point. And we do that because it's a lot easier to graph small numbers like 0 and 10 versus numbers like 1960 and 1970. So most of the time when you graph something like this, that will not be done for you. They'll give you the year, and then you have to decide what X is and make a new column for X so that you know where you're counting. Here they've done that for us. So we're setting 1960, our first year of data, as year 0. And then 1970 is 10 years later, so that now has an X value of 10. And then so you can see that we're counting how many years since 1960. So we're just resetting our horizontal values so that they're smaller. And in our graph, you have to make sure that you label that, because if you don't include that in your graph, if you're looking at the graph, the horizontal will say year, and you're like, year 0, year 5, like you're going to be thinking like way ancient times. So it's really important that you say, okay, X equals 0 is actually 1960. So you have to do a little bit of math there. You make it clear, but we do this so that we don't have such big numbers to graph. So that's X, and then it says let Y represent the percent of men and the percent of women that completed 4 or more years of college. So we have 2 columns here for Y. That basically means we're graphing 2 sets of data on the same graph. And we do this so that we can make comparisons. So we can, and we need to make sure that we're graphing the same unit. So we're graphing percent for both. And we're doing this so we can visually compare males to females on our graph. So that's why we have this set up the way it is. And this is a very common use of graphing and to do comparisons. So part A says plot the data points for men and for women on the same graph. So we want to do this in 2 different colors. And we're going to just be estimating because our graph here, or our data table, has decimals, and our graph doesn't have indications for decimals. So we're just going to estimate. And so I'm going to make, because purple was the first color I have on my pen, so we'll just do purple and then we'll do green. So I'm just color coding just so I know what color is what. So I'm going to graph men first. We're going to use the column with X, so I'm at 0, and then my Y value is 9.7. So I'm going to just graph that close to 10, because that's about what it is. It's not exactly 10, but it's very close. I'm just putting a little dot there. My next X is at 10, so I need to make sure that I'm at 10, and then that is 13.5, so that's about halfway between 10 and 15. I don't know why my other dot disappeared. There we go. So I'm just kind of estimating halfway between 10 and 15 on my Y. Then our X value of 20 is 20.1, so I'm going to graph that just slightly above 20. Then at 30, we have 24.4, so that's close to 25. 40 is 27.8, so I'm going to say that's about halfway between 25 and 30. Next, we've got 45, which is 28.9, so that's got to be a little higher than my previous one. And then 50 is 29.9, so again, that's going to be higher. So I just got to make sure that I make those look higher. Now, when we're graphing things, if you just graph the dots like this is called a scatter plot, but it's usually easier to see trends if you connect the lines. So I'm going to do my best to connect these as best I can. I am not very good with eyeballing these lines, but I'm going to try my best. And when you connect them, that is called a line graph. So a scatter plot does not connect them. A line graph does. A line graph is nice because you can kind of see the trends rather than just a series of dots. So now I'm going to do the same thing with my Y, which is the women. So I'm going to start at 0, which is 5.8. So I'm just going to sort of estimate where that is. 10 is 8.1. 20, 12.8. We got 30, which is 18.4. 40 is 23.6. So I'm just estimating here. I'm not getting it exact. 45 is 26.5. And then 50 is 28.8. And so now I'm going to start eyeball. So you can kind of see the trend. And when you connect them, it makes it easier to see that for many, many years, there were fewer women with 4 or more years of college than men, but they were basically after 50 years, so 2010, they're almost caught up to men as far as percent. So it gives you can see the trend there, and you can see clearly males are higher, there's a higher percent of males than females with 4 or more years of college for most of this time period. So that's part A. And then part B says, is the percentage of men with 4 or more years of college increasing or decreasing? So that's basically is this increasing? Is the graph getting higher as time goes by, or is it getting lower? So we can see that it's getting higher, so it is increasing. And then is the percentage of women with 4 or more years of college increasing or decreasing? That is also increasing because it's going up as time goes by. So that's an example of where this comes in handy. And in later sections, you learn how to basically make equations for graphs like this. If they make a line, you basically learn how you can make an equation that you can use to predict the future based off of past data. And that's where algebra is really handy, is making equations of lines and then using that for prediction based off of trends that you've seen before. So that is my last example here.